Welcome to this new session. In the last class, we discussed about the definition of a dimension, and we discuss some common dimensions, and in the end, we discuss some dimension of some subspaces of a vector space. We know that the common dimensions we calculate Rn, Pn, and any matrix m by n matrices. In this class, we try to prove one or two important results regarding the dimension of a vector space, which help to us to define the basis of a vector space. And there is one of the result which saying that if we have any finite dimensional vector space, then is form a basis if it is a linearly independent. This means there is no need of we have to calculate the span of a set is there. So let's start with the first results. This result we already proved in the two class before, where M is a n dimensional vector space be the set of a linear independent. We just take not n dimensional, we take any vector space and n elements, and then it's linear independent, and then we have take some m elements with m is greater than n, then m this is always is the linear independent. Yani every n plus 1 elements is set is a linearly dependent. Now we have to using this result, not we have already proved this into the previous classes. Okay, now we have to start with this. Let V be a finite n dimensional vector space. So this means we have a giving dimension of a V. V as a dimension of a V is we have a giving n, and it says any linearly independent set n vectors. So we have to just check we have a given what this set is a n vectors, and this n vectors is a form a basis. Means there is a no need if we have a finite dimensional vector space. So if we just check these vectors, n vectors are linearly independent, then we can say that this form a basis of vector space. That means there is no need of a we have to check is a span or not. So by this we just said that because we have a already this set is giving n vectors are linearly independent, but we have to form a basis, and because we have to form a basis means we need to show that the span of any suppose we just take a V is equal to we have a V1 V2 up to Vn. This is a set of n vectors. This is a linearly independent vector. Now we have to show that this is the basis, means this B is automatically is linearly independent, already is there. Now we have to show that the span of this B is equal to this V is there. So we try to solve this. B is a automatically B is linear independent. Now we try to solve that span of a B is equal to V. That means suppose B is equal to V1, V2, V3 up to Vn. B is a set of n linearly independent vectors. To prove B is a basis, we only show that the span of B is B spans V, span of a B is equal to V. This means we have to just show that span of a B is equal to V. So let we start from the we take a let any element W, arbitrary element from the vector space V, and now we have a since dimension of a V is equal to we have a n. So if dimension of a V is equal to n, then means we have the set, we have a set of the form of a W V1 V2 up to Vn, and this of n plus 1 vectors, and this is clearly is linearly dependent by the lemma. We just said that every n plus 1 vectors of a n dimensional vector space is linearly dependent. So we can say that this Vwn is linearly dependent. That means there exist scalars alpha 1 alpha 2 up to, sorry, we just take alpha also, alpha 1 alpha 2 up to alpha n, not all 0, not all 0. So we just write alpha times of a W plus alpha 1 V1 and so on, plus alpha n Vn is equal to 0 vector, where at least one of them alpha 1, alpha 2, alpha n is equal to 0. Now if we have a possibility, suppose alpha is equal to 0. Now if alpha is equal to 0, then what we getting, we have to, because alpha is equal to 0, 0 of w is equal to, we have a 0, and then we can say that in this case we can say that alpha 1 v1 plus so on, alpha n vn is equal to 0, and because this set are, and also we have to assuming this scalar, if we take a alpha is equal to 0, then one of them alpha 1 up to alpha n, at least one of them is not equal to 0. If this alpha, so this means alpha 1, alpha 2 up to alpha n not all 0, so at least one of them is not equal to 0. If one of them not equal to 0, this means this set is linearly dependent, and if this set is linearly dependent, that means we have a given v, b set v1, v2, vn is independent vectors, which is contradiction, so we have a contradiction. So that means clearly alpha should be not equal to 0. So alpha is not possible, alpha should be a 0. So if alpha is not equal to 0, then what if we have just said that if alpha is not equal to 0, then alpha w can be written as a minus alpha times of a v1 and plus so on minus alpha n times of a vn is equal to this is equal to this thing. And now alpha is not equal to 0 means alpha is not equal to 0. This 1 upon alpha is also belongs to R. This is element of R. So this we have to multiply it throughout by 1 upon alpha, and then you have alpha into 1 upon alpha is equal to identity. So this is equal to 1 into, and you have 1 into w is equal to w. So this can be written as a w is equal to minus alpha 1 upon alpha v1 plus so on minus alpha n upon alpha vn. And if we have to write, alpha can be written as a finite linear combination of the elements of a v1, v2, vn, and that means this implies that we have a w belongs to the span of b, and then we have a just a w is the element of a v. So this means span of a v generate the whole the set of a this thing. So if the span of a v generated whole of the set of a v, then we can say that the set b is a linearly independent. Is from a basis of a vector space V. So we just say that suppose there exists a vector w in U, and we have to just take w not dimension, because there is a n plus 1 vectors, and this n plus 1 vectors. So this means there exists at least one of them is not equal to 0, and then alpha 0, this 0. So we have to adding 0 here. So this is giving this is a 0 vector, and then this at least this one of them is not equal to 0, which is not possible. Why? Because v1, v2, vn are linearly independent. So all each of alpha 1, alpha 2, alpha n is equal to 0. That means our assumption alpha is equal to 0 is not correct. So that means this contradicts the linearly independent set, so which is a contradiction. So that means we can just say that alpha is not equal to 0. So if alpha is not equal to 0, so we just divide this whole thing is equal to this. So w can be written into this form, and thus the w can be written as a linear combination of the given linear independent vector this. So this means this is a span of a v, therefore this form a basis of a v. So that means now onward we can just check if we have to any set we have a given. If this set is we have to try to find this set is a linearly independent. So we have to only check that these vectors are linearly. If we have to find the show that this is a basis of a vector space. That means we have to only, if we have a finite dimensional vector space, then element of this set we have to check only the linear independent. If they are linear independent, and they form a basis by this theorem. Now one more very important result, next result, when we have to any set v1, v2, vk is a linear independent subset of a n dimensional vector space, because we have a dimension of a vector space is given. So we have here we can say that dimension of a v is equal to n. So if you have a dimension of a vector space is equal to n, that means we can clearly say that this b dimension of n means this is the basis has a n element, and so this means basis has a, you have a v1, v2 up to somewhere is a vk and so on vn, and this b is you have a linearly independent, and also because of a this we can say that span of B is also is equal to V. Okay, so now what is this theorem is suggesting that is saying that if we have a subset of a linearly independent n dimensional vector space, he said that then we can find a n plus 1 vector, find a n plus v times k plus 1 vector up to n vectors in V such that v1, v2, vn is a basis. Means we have to, if we have a vector spaces given, and we can extend the basis up to the dimension of a vector space. So this theorem is very important. If we have a some vector space is giving, we have a dimension, if giving is only space is a 2 element, if R3, then we can extend this basis up to the dimension of the vector space. How we extend the basis for a dimension means we have to choose a vector which is not belong to the span of the all the preceding element. We have a proof with the theorem. If we have a find a element which is not the span of the preceding element, then this vector with the other vectors form a linear independent set. So in the linear independent part, we have to prove this theorem. If we have to just say that, for example, if we take a vk plus 1, if vk plus 1 does not belong to the span of its preceding element up to v1, v2, vk, then we can say that v1, v2, vk plus 1 is a linearly independent. So that means this theorem suggests that we have to identify a vector which is not belong to the span of this vector. If it's not belong to the span of this vector, we can add this vector into this set, and that make is a linearly independent. So in this way, proof is also in this way. We have to write proof in the similar fashion. That means we have to find element. So since the set is a v1, v2, vk is a linearly independent subset of n dimensional vector space, so this means k should be less than or equal to n. So because dimension is equal to n, this is a subset. So this k is exactly value for k is less than or equal to n. So suppose if first is very trivial, if k is equal to n, then we are done. Because if we have a k is equal to n, then clearly this v1, v2, vk, and then these vectors are linearly independent already is given, and then because of this finite dimensional and dimensional vector space, so that means we can say that by the previous theorem, this is form a basis for a vector space V. Now if k is less than n, then what is this? If k is less than or equal to 1, then v1, v2, vk is not a basis for V clearly. So this is if dimension k is not equal to n, is not equal to the dimension of this, that means clearly this is not a basis. Why is not a basis? Because if k is less than or equal to n dimensional vector space, in this vector space in basis we have a n element, and then n element are linearly independent, also span of this we generate whole the vector space, and in the vector space we have a n element. So this means the span should be the equal to b only when we have a v1, v2, vk, and if we have a k less than strictly less than n, then we have a clearly is not a basis. But these vectors are you have a linearly independent. So we have a given these vectors k are linearly independent and is not a basis, means there is only condition which is happening in this. We have to just say that span of these vector v1, v2 up to vk is not equal to the v, means the span is not the same as generate this whole things is there. So that's what this thing means. We have to find one element which is does not belong to the span of this, and then we have to just show that by this thing. So because I just said that v1, v2, vk is linearly independent, therefore the span of a v is clearly is not equal to v. Hence this is a proper subset of a v. Is not we have to let, because we have to show that span of a this is equal to v, but the span of a v is not equal to v. So that means we can say that the span of this set is a proper subset of a v. So what we choose? We choose a one element which is does not belong to the span of a this. So we have to arbitrary, we suppose vk, so we can choose a vk plus 1 is not belong to the span of v1, v2 like this vk. If we have to find this vk plus 1 is a such a way one element, if we find a vk plus 1 is a such a element where it does not belong to the span of a v1, v2, vk, then we can say that the set this v1, v2 up to vk plus 1 is linearly independent. And if again this k plus 1 is equal to n, then we are done. If k plus 1 is not equal to n, then again this set is a proper subset of a span, is a proper subset of a this. Then we have to find another element v of k plus 2 is not belong to the span of v1 up to vk, k plus 1, and then we have to construct the set this v1, v2, vk, vk plus 1, vk plus 2 is linearly independent. Again vk plus 2 is equal to, we have n, then we are done. If it is not, then we have to find another element in this way. So okay, so does there exist any non-zero vector? We have to choosing v, because we have to choosing non-zero. If 0, there is a linear dependent, so this is not contradictory. So vk plus 1 is the element of a v, such that vk plus 1 does not belong to the span of a this. If vk does not belong to the span of a this, means what we say that, it means we have proved this theorem in a linear independent. If we have any element does not belong to the span of all the preceding elements, then this new set v1, v2, vk, vk plus 1 is linearly independent. By that result, we can say that this set is a linearly independent. So if this set is a linearly independent, means we can say that clearly, otherwise the vectors, if not, then what is this? This is vk, say vk is in the span of the preceding, and if vk in the preceding preceding element, why not the v2, v3, vk, because of this is I think v1 is missing, no problem, v2, v3, vk, because none of them cannot be possible, because these are vectors are linearly independent, and the scalars of this is equal to clearly 0. So only possibility is equal to this vk. So vk is in the span of its preceding elements. So this means if ak plus 1 is equal to n, we are done. If it is not, then we have to, again we can say that the span of v1, v2, vk, sorry, एक minute, vk plus 1 is not equal to v, means again this is a proper set. If it is again is a proper set, we can find another vector vk plus 2, which is does not belongs to the span of v1, v2, vk, vk plus 1, and if it is done, then we can say that the set v1, v2, vk, vk plus 1, vk plus 2 is linearly independent. And if k plus 2 is equal to n, we are done. If it is not, we have to repeat the same process again until we get in the n linearly independent set of vectors. Okay, so if it is not, we repeat the foregoing process until we get n linearly independent vectors v1, v2, vk, n, and that this form a basis for a vector space V. Okay, so this complete the proof of this theorem. I just say that more elaborate this theorem by the example. Suppose we have given two linearly independent vectors of R4. We have the dimension of a, you know that R4 is equal to 4. So this means dimension of a R4 is equal to 4. So we have giving these two vectors. I just say it as V1 and V2, and these two vectors are clearly linearly independent because none of them is a scalar multiple of a other. If it is these two are linearly independent, then we can write the span of these two vectors. So we have to write first by the theorem we use in this form. We have to write the 1 0 1 0, and then we have a 0 minus 1 1 and 0. We have to write the span of this. Now span of this is the form of this. We have a alpha times, so we have a 1 0 1 0 plus beta times of a 0 minus 1 1 0, such that alpha and beta are the element of a R, and this can be written in the form of a, we have to write in this form is equal to, we have a alpha and we have a minus beta, alpha plus beta, and we have a 0, such that alpha beta is the element of a R. So span of these two vectors into this form. Now we have to choose, because there is these two vectors are linearly independent, but dimension is equal to 4. So we choose another element which is not belong to the span of this, means this thing. Now see, this is the first element, second element, the third element is what is alpha plus beta, or we can just remain this, we have to just go to this last element first, and then we have to calculating this. So last element, just you just check this is equal to, you have a this element, sorry, we have a this element is equal to 0, and then if we choose an element like this 0 0 0 1, it's a non-zero element in the last position, this is clearly is does not belong to the span of 1 0 1 0, and we have a 0 minus 1 1 0. So this means clearly this does not belong to the span of this. That means the set we can extend in this form. We have a 1 0 1 0, and then we have a 0 minus 1 1 0, and then we have a 0 0 0 1, and clearly this set is a again is a linear independent, and but still is not, because there is a element is equal to 3, and in this case we have to basis is a 3 element, and this dimension of this set is equal to, you still is equal to 3. So you need is not equal to 4, so we need one more vector to add, and this that means we have to write the linear span of these 3 vectors and choose a vector which is not belong to the span of this vector. So okay, this one first we have to write into this form. Now span of 3 outside, by the previous theorem we choose a vector outside of a span of this and extend the linearly independent set. Since the fourth coordinate always is a 0, for this vector certainly is not belong to the span of this set. So we have to write this. Now what is the span of these 3 set? Span of these 3 set is this form, alpha plus beta plus. Now you choose this third element. Is the third element is the form where sum of a first and 2 elements. So we have to choose an element where this not the sum of these 2 elements. So we choose any element arbitrarily in the set which is not the sum of a first 2 elements, and this there is no need of this. So we have to choose any scalars which is not the sum of this. You take a element of like this, I just took a, this is have identity, one element outside the span. So alpha beta gamma, the third coordinate of the element span is always is equal to alpha beta. So we look for a vector which is not true for this. So in this span means we have to choose an element which is clearly say that the sum of the third element. So we have to choosing element like this 1 minus 2, because 1 plus minus 2 is equal to, you have a we have to just is equal to we have to check the sum of this. So 1 plus minus 2 is equal to minus 1. So here I just take a 0, not a minus 1. So this clearly this is not belong to the span of this set. And now if it's not belong to the span of this set, so we have a set is this, and then you can not necessary you have to choose this element. You can choose any element. I say 2 3 7, and we have to take a 0, because 2 plus 3 is equal to 5. I choose a element which is not equal to the sum of a first 2 elements. So if the sum of these two, clearly we have to choose such a element. This is the belongs to the, maybe this is the one of the element which is the element of this, or also we can choose, you have a 1 0 2 0. This is also which is we choose in a such a way which element not belong to the this content, and this the sum of these two is not here. So this means we take a this way, and in this way we can say that this set B is a linear independent. And now because basis is a 4, now we cannot find any other element of this, because we have every n plus 1 vector form this B set is a linearly dependent. So we cannot find any other element to extend this basis. So we have to getting the 4. So this means we can say that by the theorem we have to find a basis which is a linearly this extend to the basis. This is very important concept for extending the basis. So it's very trivial. We just take a whatever linear independent vectors, and then we write a span of these vectors, and in the span we have to choose what types of element in the span. and we choose any element which types this is not does not belong to the span of this. If it is the element is not belong to the span is this, then we have a theorem. If it does not belong to the any span, then this element include the previous element make a linearly independent set. So this one of the example. Now I just take a one more example, and again try to extend this basis. So I one more 1 1 1 1. So we have a clearly these two vectors are linearly independent, because uh, for two vectors linear independent if none of them is a scalar multiple of a each other. So one this one is not equal to the true, so this means clearly these two vectors are linearly independent. So we write a span of these two vectors. So span of 1 1 1 1, and then we have a 1 2 1 2, and this can be written in the form of a, you have a, we have to write a alpha plus beta, and then you have alpha plus 2 beta, then you have alpha plus beta, alpha plus 2 beta, and then we have a such that alpha beta are the element of R in this. So now you see that the first and third R elements are the same. So we can choose any vector which is not the this place is a differ. So we just choose a 1 0 0 0. This is clearly first and third elements are differ. So we can just which is choose which is clearly is not the element on any other element. So this we just the alpha plus beta, and this are the scalars. So we just choose a, since the first and the third coordinates are equal, all vectors span. So we have a 0 3 2 0, and it is not the span of this, thus we have an enlarged extended set is this, and this set is linearly independent. Okay, so this set is linearly independent, but if it is form a dimension basis, then this dimension is a 3. So this means we again one more vector need to extend this. So we find write a span of this span of these three vectors. Now you see now you see that this the second, and you have a last elements are the same, second and the fourth vectors are the same. If you have a second and fourth vector are the same, then we can choose any element which is contradicting these two positions. So then we have to suppose we have a this is second is equal to 5. So I choose this is equal to 6 and 5, two different, because here we have just check this second position, and then you have a fourth position remain the same. So I differ these two position, and if we differ these two position, then we have a the vectors this 2 6 4 5 is not in this span. So hence we can say that these vectors are clearly these vectors form a set of linearly independent, and here because of this set is linear independent, now this in the it is a basis, and because the finite dimension, and this basis has a, we have a 4 element, and this is the same of a dimension of r to the power 4. So this way we can extend the basis of any vector space. So we just say if we have a vector space is given, we have a linear independent sets are there. So we have to try to write the linear independence of these vectors clearly in this way. We write a span of this, we choose a vector which is not does not belong to the span of a dash set, and if we find such element, we add this into the two linear independent three linear independent set vectors, then a new set of vectors is clearly is a new set of a vectors is back a linear independent, and in this way we have to extend the any number of a basis of a given this. Okay, so thank you for your this lecture. In this lecture we prove two very important result. One, the result is this: if we have a finite dimensional vector space, and then for a basis we have to just check the linear independence. And in the second theorem we try to find that if we have a proper subset of a linear independent vectors, we can extend this basis up to the basis of the vector space. And in the end, we have to discuss two examples of in this case. So in the next class, we discuss about the very important theorem regarding the dimension theorem, where is a dimension of a sum of a two subspaces can be written as a dimension of a if u and w are the two subspaces, the dimension of a sum of a u plus w is equal to dimension of a u plus dimension w minus dimension of a intersection. Okay, thank you.